let us begin this lecture by two definitions. So first definition is a convergent sequence in a metric space. Convergent sequence in a metric space. Let us recall the definition of convergent convergent sequence. Okay, so we all know that a sequence is a function whose domain is the set of positive integers. Okay, now let xn be a sequence in a metric space, say xd. Okay, d is metric on x. We say xn converges to a point, say x naught in x, if for any epsilon positive there exists a natural number or a positive integer, say n naught, such that whenever n is greater than equal to n naught, when n is bigger than n naught, what we get is distance between xn and x naught is less than epsilon. Okay, this is first definition. Now let us see another definition. Definition of a continuous function. Definition of a continuous function. So let us define continuity. So, continuous function from a metric space to another metric space. So let xd and say y row be two metric spaces, and f is a function from x to y. We say f is continuous at a point, say x naught in x, if given epsilon positive, if for given epsilon positive there exists a delta which depends on epsilon and x naught, such that uh, such that whenever distance between x and x naught is less than delta, we will get a row of fx. Distance between fx and fx naught is less than epsilon. So this is the definition of continuity. So what we observe in these two definitions. So this is second definition. What we observe in these definitions is that they are dependent on the metric structure. Okay, so here you see we are using metric on x. Here also we are using metrics on x and metric on y. Okay, so now let us ask a question. Can we somehow eliminate this dependence? So this dependence on the metric in these two definitions. in these two definitions. So let us analyze these two definitions. So first, let us analyze this definition. Okay, convergence. So let us first analyze or say analysis. So when we say a sequence is convergent and converges to a point x naught, then we are saying for every epsilon there exists a positive integer n naught such that distance between xn and x naught is less than epsilon whenever n is greater than equal to n naught. What does this mean? Okay, good. So let us define a notion that is called epsilon neighborhood. Epsilon neighborhood of a point of x naught. So what is epsilon neighborhood of x naught? Recall, so we already know this from metric space. So this ball centered at x naught and radius epsilon, okay, it's called epsilon neighborhood of x naught. So it is defined like this: all x in x such that distance between x and x naught is less than epsilon. Okay. So what we observe from from this definition, what we observe from this definition is the following. We observe that for every epsilon there exists a naught such that this happens. Okay, such that this happens. Now, what does this mean? This means every epsilon neighborhood of x naught contains all but finitely many xn's. Okay, you see here, after a certain stage, after this n naught terms, all terms are in this epsilon neighborhood of x naught. Okay, so in this way we can define a convergent sequence where we will not use uh, the term metric. Okay, so let me write this definition again. So definition: a sequence xn in a metric space xt is said to be convergent and converges to say x naught if every epsilon neighborhood of x naught contains all but finitely many terms, but finitely many terms. Okay, so in this definition we didn't use uh, the metric d. We replaced that by this epsilon neighborhood notion. Okay, now let us come to second definition, that is definition of continuous function. So So recall that in that definition of continuous function, it was written that for every epsilon positive there exists delta positive. Delta depend on epsilon and the point x naught. Okay, such that whenever we have this thing, we will get this. Okay, so let us rephrase this definition in terms of epsilon and delta neighborhoods. Okay, so for every epsilon positive, we have this. So recall the definition of epsilon neighborhood of fx naught. Yeah, so be fx naught epsilon. It is nothing but all those uh, y in y such that row of y comma fx naught is less than epsilon. Okay, this is the definition of epsilon neighborhood of x naught. Similarly, the delta neighborhood of x naught is all those points of x such that the distance between x and x naught is less than delta. Now we rephrase this definition. Okay, let f from a metric space xd to another metric space y rho be a function, and say x naught be a point in x. We say if it's continuous at x naught. If see here, for every epsilon we have this. This means if for every epsilon neighborhood, say u, epsilon neighborhood u of fx naught, there exists a delta neighborhood v of x naught. So you see this u, this epsilon neighborhood u, this is subset of y, and this v is subset of x. Okay, with this property such that f of v is contained in u. Okay, so you see we have removed the dependence on the metric, and we rephrase this definition in terms of epsilon neighborhood. Okay, so this is another way. So these two definitions are equivalent. Okay, and here we do not need any any distance. Okay, now let us recall a few definitions from metric space. So let us recall the definition of open set. What is open set? A set S, or say a set U in a metric space. Okay, let me write like this. Uh, a subset U of a metric space X is called an open set. It's called an open set. if for each point x naught of x, there exists an epsilon neighborhood of x naught, say epsilon neighborhood be x naught epsilon of x naught, such that this neighborhood is entirely contained in U. So this is the definition of open set in a metric space. In other term, in other words, we can say, in other words, we can say a subset U of x is open in X if U is a neighborhood of each of its points. Okay, this is another similar type. These two are equivalent. Now we can rephrase this definition, this and this definition. We can rephrase this definition. So so in new definition, so a rephrase or say paraphrasing paraphrasing of definition of convergent sequence. So a sequence xn in a metric space X is said to be a convergent sequence, and converges to say x naught if every open set U containing x naught contains all but finitely many xn's. Okay, so this definition is in terms of open sets. Similarly, we can paraphrase the definition of continuous functions. Second definition: a function from a metric space X to another metric space Y is continuous at a point x naught in X if every open set, okay, if for every open set, say U containing fx naught, there exists a neighborhood or there exists an open set B containing x naught in X, okay, with the following rule such that f of V is contained in U. Okay, so now we have defined uh, continuity in terms of open sets. So why are we interested in these definitions, and why are we interested in open sets? Okay, now we want to, so in mathematics, you know, in say in real analysis or in metric space, this uh, continuity was a central part of analysis. Okay, similarly the convergent sequences, uh, these were also a central part. So now if we have complicated spaces where these metrics are very complicated, uh, there we can use these definitions. Okay, now we will our aim is to to generalize this definition to some other complicated spaces, or say more general spaces. So what is a space? Space is a set with some structure. Like metric space is a set with a metric structure. Means uh, metric d, that you know, that is a distance. Similarly, a vector space structure. What is vector space? Vector space is a set with algebraic structures. Okay. So similarly, we want to generalize these things. So our aim is uh, to give you to give you a definition of topological space. Okay. So to define a topology, why we are defining topology? Because we want uh, get rid of the dependence. So the dependence on metric. Okay. So we want to say that the continuity and the convergent sequences, uh, they, they should not depend on metric. Okay. So here we have a choice. We see, if we somehow define open sets on any set X, then we can define continuity. Similarly, we can define convergent sequences. Okay. So given an arbitrary subset, given an arbitrary set X, how do we say a subset of X is an open set? How can we say a subset of X is an open set, in X? For this, let us recall a result from metric space. Okay. So result says, you all know. So I will not prove this result. You all know this. So it says that empty set and the whole space X, these are open sets in X. Okay. Secondly, finite intersection of open sets is open in X. Third one, arbitrary union arbitrary union of open sets in X is open in X. Okay, we have these three definitions. Taking Q from this result, we define topology on a set. Definition. Let us see our definition. So our aim is to uh, give a meaning to open set. Okay, what is an open set? We want to define that in an arbitrary set. So for that, let say X be, let us take X a non-empty set. Okay, be a non-empty set, and let us take tau a collection of subsets of X. Subsets of X. Okay, we say tau a topology on X if the following holds. If the following holds: number one, empty set and X both are members of tau. Means empty set and X belongs to tau. So this is in this collection. Secondly, suppose U and V be two members of tau, then their intersection is again in tau. Third property, if we have an arbitrary collection of open sets, an arbitrary, so we have arbitrary number uh, of elements coming from tau. So U alpha is member of tau. So alpha be any indexing set. Alpha is coming from any indexing set lambda. Okay, so if this, then so this is an arbitrary collection of members coming from tau. Then their union U alpha is in tau. Okay, if these three properties are satisfied, then we say tau is a topology on X. Okay, so now you see these three properties are nothing but these three properties of open sets in a metric space. Okay, so we will say, note that members of tau are called open sets. Okay, we will name these members as open set, and and so members of X are called, these are called points. Okay, or elements of X are called points. Okay, so let us see some examples first. Examples. So, first example, from above discussion, we all know at least one example of a topology. Uh, okay, let me also say something in above definition. So as you know, XD was called metric space. This order pair X with tau, this structure is called topological space. This is called topological space. Okay, X tau is called topological space. So first example, every metric space is a topological space. Every metric space is a topological space. Okay, so how? So see, for topological space, we need a set and a collection of subsets which satisfy these properties. So a metric space is a set with metric structure. So we will take the same X. Okay, and for tau, what we will do? We will take tau will be the collection of all open sets in X. Okay, we know X is a metric space, so we all know it's open sets, and we will take the collection of all open sets in X. Okay, and you know from this result that three properties are automatically satisfied by open sets. Thus, X tau is a topological space. This topology tau and tau is called topology generated by the metric D, okay, topology or topology induced from D. Okay, good. This is one example. Now another example. So second example. Okay, let us take X be a singleton set. Say this set containing one. So we want a topology on X. Okay, but for tau, what we know that empty set and X is there. These two should be there. Okay. Is there any other subset of X? No, these are only two subsets. Okay, these are only subsets of X. So this will be the topology. So there is only one topology on on singleton set. Now let us take set with two elements, say A comma B, and let's see how many topologies can be defined on this set X. So say first topology where we have only two subsets, empty set and X. Okay, so here also we have this set, this topology in both cases. So this topology has a name, a topology which has only two open sets, empty set and X. This is called trivial topology. Trivial topology or indiscrete topology. Okay, so this is trivial topology. What is second? Is there, so empty set and X would be there, then we can take A. This is also a topology. Say uh, intersection of these two is A, it is already there, and union of these subsets is X, it is already there. So it is easy to see that tau 2 is a topology on X. Similarly, this is also a topology on X. Is there any other topology? Yes, there is one more topology. Phi X A P. Okay. So see, in this topology we have taken all subsets of X. Okay. This topology is called discrete topology. Discrete topology, and these topologies are called Sierpinski topology. Okay, so now here is an exercise for you. Exercise. Find all topologies on this set. Okay, so you do this and we will meet tomorrow.